Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Heat and Thermodynamics by Brijlal and Subramanya. We'll continue to discuss topics from Module 3, Thermodynamics. We will start with a brief discussion on Maxwell's thermodynamic relations. This is actually not a part of your syllabus, but to learn the next topic, you need to have some basic understanding about Maxwell's equations. So as we all know, the state of a thermodynamic system can be characterized by a set of four state variables: pressure, volume, temperature, and entropy. So all the relevant parameters related to the thermodynamic system you can express in terms of these four variables. For example, if you look at internal energy, the total energy content of your system, from second law of thermodynamics, we know that dq equal to du plus dw, or change in internal energy, du equal to dq minus dw, where dq is the exchange of heat and dw is the amount of work done. And dw equal to pdv, so du equal to dq minus pdv. From the chapter on entropy, we have seen that change in entropy ds equal to dq divided by t, or dq equal to tds. So the change in internal energy du equal to tds minus pdv. So you can describe the change in internal energy completely in terms of these four variables. Same way, there are other important parameters like Gibbs free energy or Helmholtz free energy, enthalpy. So these are the important thermodynamic potentials, and all those you can describe completely using these four state variables. Now, considering two state variables at a time, you have six possible combinations: pressure and volume, pressure and temperature, pressure and entropy. Same way, volume and temperature, volume and entropy, and finally temperature and entropy. And you can write a thermodynamic relation connecting any of these pairs. For example, if you look at the first pair, P and V, we know there is a relation work done, dW equal to pdV. Same way, if you take the last pair, temperature and entropy, we know that change in heat energy, dQ equal to TdS. Okay, so same way for any pair, you can write a thermodynamic relation. Since we are already familiar with the first and last pair, let's remove them. Now we have four pairs: pressure and temperature, pressure and entropy, volume and temperature, volume and entropy. Now you can write a thermodynamic relation corresponding to each pair, and this is known as Maxwell's thermodynamic relations. We are not going to get into the details of the derivation. We'll just look at the final results. In fact, you don't even have to know the final result. Okay. The first relation, dou T by dou V at constant S. So change in temperature as a function of volume at constant entropy. This is equal to minus dou P by dou S at constant volume. So negative of the change in pressure as a function of entropy at constant volume. Similarly, the second thermodynamic relation of Maxwell, dou S by dou V at constant temperature equal to dou P by dou T at constant volume. The third relation, dou T by dou P at constant entropy equal to dou V by dou S at constant pressure. And finally, dou V by dou T at constant pressure equal to minus dou S by dou P at constant temperature. So you don't have to by heart any of this relation. But why did I introduce this topic? Because unless you know Maxwell's relation, you won't be able to understand another very important equation in thermodynamics, which is part of your syllabus. This is known as Clausius-Clapeyron latent heat equation. And the derivation of Clausius-Clapeyron equation comes from Maxwell's second thermodynamic relation. So if you look at the second relation, you have a change in entropy as a function of volume at constant temperature equal to change in pressure as a function of temperature at constant volume. Now, what's the meaning of this? When you provide heat energy to a system, you know that its entropy increases and also the volume is going to increase. The gas expands, right? So you have a positive relation on the left hand side. This being an equation, you should have a positive relation on the right hand side. Let's see whether this is true. When you increase temperature of a gaseous system, so ideally its volume increases, but if you keep the volume constant, what happens? The pressure is going to increase. So you have a similar positive relation on the right hand side also. Now you multiply both sides with temperature. So you have T into dou S by dou V at constant temperature equal to T into dou P by dou T at constant volume. Now we know that T ds equal to dq, right? Now instead of a total derivative ds, we have a partial derivative dou s. Right? So you have, instead of dq, you have dou q here. So dou q by dou v at constant temperature equal to T into dou p by dou t at constant volume. Now what's the physical meaning of this equation? If you look at the left hand side, dou q by dou v at constant temperature represents the amount of heat exchange per unit change in volume at constant temperature. So this heat absorbed at constant temperature is known as latent heat. We have discussed about it in one of the previous classes, right? So latent heat is the heat absorbed when a substance changes from a solid state to liquid state, or from liquid state to gaseous state. So basically, when there is a first order phase change like this, there is a change in volume, but the temperature remains a constant. I hope you remember the phase diagram. So if you plot a diagram between energy input or heat supplied and temperature, you can see that suppose you take a piece of ice, supply heat energy to it, its temperature increases. When it becomes zero, it starts melting, and during this time, when you supply heat energy, the temperature doesn't increase. So basically, ice gets converted into water at the same temperature. The temperature of ice as well as the temperature of water remains the same. So during this point, temperature remains a constant. Once the entire ice gets converted into water, now the temperature starts increasing as you supply heat. When it reaches the boiling point, 100 degrees Celsius, once again, when you provide heat energy for some time, the temperature doesn't increase. So basically, the water gets converted into steam at the same temperature. Temperature of water and temperature of the steam, both are same. Once the entire water gets converted into steam, once again the temperature starts rising as you increase the heat energy. So there are two phases here, or two regions, where the temperature remains a constant even though you are supplying heat energy, right? And these two regions corresponds to phase transitions. So in the first region, the solid phase is getting converted into liquid phase, or this is the melting region. Similarly, in the second region, the liquid phase is getting converted into gaseous phase. This is the vaporization region. So during these two processes, phase change is happening and the temperature is remaining as a constant, right? So in such cases, the heat absorbed or released is known as latent heat of the material. So you can define latent heat as the thermal energy absorbed or released by a thermodynamic system during a constant temperature process, such as first order phase transition. Now, from this equation, now I know that since temperature remains a constant, the amount of heat exchange dou Q equal to the latent heat L. Okay. So this dou or delta, both of these indicate a change in heat. Usually when you write dou or d, it represents a small change as well as a continuous change, small continuous change in heat. On the other hand, when you write delta, it represents a discrete change, usually a large change, large discrete change. Nevertheless, d, dou, delta, all these represent a change in a parameter. Okay. So since we have a finite change here, instead of dou, I am going to write delta Q. So delta Q equal to latent heat F. Similarly, the volume change, let me say the volume of one of the phases is V1 and the volume of the other phase is V2. So change in volume delta V equal to V2 minus V1. And we are considering a unit mass of material here. So when I make these two substitutions in this equation, the left hand side becomes L divided by V2 minus V1, which is equal to P into dou P by dou T at constant volume. Now pressure depends on two variables, temperature and volume. That's why I wrote it as a partial derivative. Whenever a function depends on more than one variable, you write it as a partial derivative. But one of the variables is fixed here, which means P now depends only on temperature. So the partial derivative gets converted into a total derivative. So the right hand side becomes T into dP by dt. Or when I take temperature to the left hand side, I get dP by dt equal to L divided by T into V2 minus V1. This is known as Clausius-Clapeyron latent heat equation. Now what's the meaning of this equation? When there is a change in pressure dP, the boiling point or the melting point of the material is going to change. Right? That's what is indicated by this equation. Boiling point or melting point, this is not a constant, this varies as a function of pressure. Let's see what is the implication of this result. First, let's discuss about the case of vaporization. The effect of pressure on boiling point of the liquids. So whenever a liquid gets converted into gas, the volume of the gas is always greater than the volume of the liquid. So if you take volume of gas as V2 and volume of the liquid as V1, V2 minus V1 is always positive. So if you go back to the Clausius-Clapeyron equation, V2 minus V1 is always positive, latent heat is also positive, and temperature, since we always take absolute temperature with respect to 0 Kelvin, this is also positive. So basically the right hand side is always positive, which means the left hand side has to be positive. So dP by dt is positive. And what's the meaning of this? Whenever there is an increase in pressure, when dP is positive, the boiling point also increases. dt also is positive. Right? So when pressure increases, boiling point increases. You will see several manifestations of this in your daily experience. We know that typically water boils at 100 degrees Celsius, right? But I cannot simply say 100 degrees Celsius because now I know that boiling point is a function of pressure. So I need to specify at what pressure water boils at 100 degrees Celsius. Typically, water boils at 100 degrees Celsius at a pressure which is 76 centimeter of mercury. This is one of the units of pressure. This is not a very straightforward unit. And what's the meaning of this unit? This is the pressure exerted at the base of a tube which contains a column of mercury of height 76 centimeter. You can convert this into a more standard unit. We know the SI unit of pressure is Pascal. 1 Pascal is 1 Newton per meter square. And 76 centimeter of mercury corresponds to 1.01 into 10 to the power 5 Pascal. Or if you want to use a more familiar unit, this is equal to 1 atm, 1 atmospheric pressure. So water boils at 100 degrees Celsius at 1 atm pressure. But in open vessels, when you cook, the pressure is less than 76 centimeter of Hg, which means the boiling happens below 100 degrees Celsius. So typically in open vessels, boiling happens at around 80 degrees Celsius. On the other hand, if you use a pressure cooker, inside the pressure cooker, the pressure is very high, which means according to Clausius-Clapeyron equation, the boiling point of the water increases. The boiling happens at a higher temperature, typically around 110 or 120 degrees Celsius. So in the case of a pressure cooker, cooking happens at a much higher temperature compared to an open vessel. That's why cooking with pressure cooker is a lot faster compared to an open vessel. Same way, if you compare a closed vessel and open vessel, which one is easier to cook? Of course, our experience tells that the closed vessel is easier to cook. Now, what's the reason? Inside the closed vessel, pressure is higher compared to an open vessel. So the boiling point increases. The cooking happens at a higher temperature here compared to an open vessel. Same way, we know that the pressure changes as a function of altitude of the place, right? Typically pressure drops as the altitude increases. So when I say water boils at 100 degrees Celsius, I said that this is at 1 atm pressure. Usually 1 atm pressure is measured at the sea level. So only at the sea level water boils at 100 degrees Celsius. As the altitude increases, pressure drops. So what happens to the boiling point? The boiling point decreases as the altitude increases. Now you can answer the question on a mountain top, whether the cooking is faster or slower compared to the sea level. Okay, so you can answer this for yourself. Now, what is the effect of pressure on melting point? So here you have a solid with volume V1 which is getting converted into liquid of volume V2. In the case of boiling point, the trend was universal because always when a liquid gets converted into gas, the volume increases. But in the case of melting, there is no universal trend. Depending on the nature of the material system, the trend could vary. So there are two possibilities. One, the volume of the liquid is greater than the volume of the solid, and there are also materials where the volume of the liquid is less than the volume of the solid phase. Let's first discuss about V2 being greater than V1. Volume of the liquid phase greater than volume of the solid phase. So from the equation, when V2 minus V1 is greater than positive, dP by dt also becomes positive. So just like the boiling point, here when pressure increases, then the melting point also increases. Example for such a system is wax. But there are other systems like ice, where when you melt ice into water and compare the volumes, you will find that the volume of ice is always greater than volume of water. So here V2 is less than V1. So V2 minus V1 is negative. Concomitantly, dP by dt also becomes negative. And what's the meaning of this? When pressure increases, the melting point decreases. So depending on the nature of the material system, pressure affects differently on different systems. On the other hand, in the case of boiling point, always boiling point increases with increase in pressure. Before winding up, let's do a quick problem. Calculate the decrease in melting point of ice produced by 1 atmosphere increase in pressure. Given that the latent heat of ice is 80 calorie per gram and specific volume of ice and water at 0 degrees Celsius are 1.091 centimeter cube and 1.0 centimeter cube respectively. Okay. So first write down the equation dP by dt equal to L divided by T into V2 minus V1. We are asked to find out the change in melting point, which is dt. So rearrange the terms, you get dt equal to T into V2 minus V1 into dP divided by L. Now write down all the parameters in appropriate unit. First, latent heat of ice is given. This is 80 calorie per gram. And what's the meaning of it? For 1 gram of ice, you need to provide 80 calories of heat energy to convert it into water at the same temperature. And you need to write it in appropriate units, preferably in SI unit. The SI unit of heat is not calorie, this is joule. So you can convert calories into joule by multiplying it with a factor of 4.184. So you have 334.72 joule per gram. Now some of you may be wondering why this gram is not converted into kilogram, because that's the SI unit of weight, right, or mass. Here this is not absolutely necessary because the amount of ice is not specified. So you can do your calculation for 1 gram of ice. So 1 gram of ice, what is the temperature change? Or if some of you want, you can calculate for 1 kilogram of ice, what is the temperature change. It is perfectly valid. So this is not absolutely necessary to convert this into kilogram. Okay, so I'm going to keep it as gram. It's your choice. Second one, what is the change in pressure dP? 1 atmosphere increase. So 1 atm change, dP equal to 1 atm. Convert this into the standard unit. So even though I told you 1 atm corresponds to 1.01 into 10 to the power 5 Pascal, that is not the correct value. The actual value is 101.325 Pascal or 101.325 Newton per meter square. You don't have to mug up all this conversion formula. I think all these conversions are given your Clark's table. You are allowed to carry Clark's table in your exam hall, so you can look up the Clark's table and get all these conversions here. Okay. Now, what is V2 minus V1? V2 is 1, V1 is 1.091. So when you take V2 minus V1, this is minus 0.091 centimeter cube. Convert this into the standard unit meter cube. You get minus 0.091 into 10 to the power minus 6 meter cube. And temperature, we are talking about ice here. So temperature is by default 0 degrees Celsius. When you convert this into the absolute temperature, you get 273 Kelvin. So make all the substitution here. All the parameters are known. So when you make the substitutions, you get minus 0.0075 Kelvin. So for 1 gram of ice, when you increase pressure by 1 atm, its melting point is going to decrease by an amount 0.0075 Kelvin. With this, we come to the end of Module 3 Thermodynamics. Thank you.